Hi everyone, welcome to the third in our educational series brought to you by Agronomist. I'm Michael DePew. We're going to talk a little bit this time about soil texture and structure. This is a little background information so we can kind of explain the mode of action of aqueous, how it interacts with soil minerals, but also how it interacts with organic material in altering soil structure and how that interplays with soil texture. So we'll just move right on. This is the disclaimer that you guys should have seen in our previous presentations. So we're presenting you with the best information we have available on our mode of action. We're still researching things, so we're not finalized in everything, but we just want to let you know that this is our best information we have so far. So we're not trying to pull the wool over anybody's eyes. So what are we learning today? So we're going to learn about soil texture structure because growthful impacts those. So we need to understand the mechanisms of it if we're going to understand about how growthful impacts it. So this is going to include things related to salt, sodium, carbonates, soil structure aggregation, and other soil quality factors that growthful is particularly suited to impact. So if we talk about soil texture, it's based on soil separates. The part that's what's referred to as the fine earth fraction. That's the less than 2 millimeter size fractions. So basically what that means, it's the size of the soil particulates, not including the gravel fraction. So it may or may not have gravel in it, but that's not included in how we determine what the soil texture is. So we just simply look at the proportions of sand, silt, and clay. And you can see there I wrote the size ranges down from each. The thing to note is for example, on your sand, the difference between your sand from your coarse to fine is like 40 times difference, and so there's quite a range there. And then I also just kind of tagged on there organic matter. Organic matter is not part of soil texture, but it influences a lot of things in the soil, so I just kind of slapped it on there a little bit. And we talk about humates too, and the thing I wanted to mention about humates is we have terms like human or fulvic acid fraction, humic acid fraction, and those aren't discrete materials. So we sometimes have people say, "Oh, I'm putting on a humic acid." Well, there is no such thing as humic acid. There are materials that fit within the humic acid fraction, and there's a range of different types of molecules that are in that fraction, but there actually is no such thing as humic acid, although and same with fulvic acid, although there's materials and that's how they're labeled, but technically that's wrong labeling. So again, this is talking about some texture. So what do we mean for sand? So sand is a size range, like I said, it's 2 millimeters down to 0.053 millimeters. That's a 40x difference. But if we look at what sand means as a texture means that greater than 86% of that soil is composed of sand. So sometimes people say sand because they're meaning it's all particles that fit within that certain range, or they're talking about sand in terms of a sand soil, which is a textural class. And then we have groups. So we have a soil textural group. So we say sandy soils. What sandy soils means is that we're greater than 70% sand and includes two soil textures, a sand texture and a sandy loam texture. Now if we look at silt, silt is a size range as well. There's no mineralogy attached to it or anything. And it's a 26.5 times diameter range within that material. But we do have a texture class, a silt texture class, and basically it's 88% to 100% silt. Now, clay is a little bit different. Clay is a size, clay is a texture, and that texture ranges from all the way from 40% clay up to 100% clay. So you might say, well, why can you have less than half of that soil is composed of clay, but yet we're still going to call it clay in terms of texture? And that's because clay dominates. When you have enough clay in a blend with the other soil separates, it dominates the characteristics of that soil. And so therefore, that's why it goes all the way down to 40%. So in terms of a textural group, which is called clayey, that includes the textures of silty clay, sandy clay, and clay. Now, what's different about clay from the other, from sand and silt, is that clay also describes a mineralogy in many cases, and clay minerals. So we have these minerals that they're referred to as clay minerals, and they have different properties: smectites, iolites, and kaolinite. Those are layer silicates. Those are the ones that give you cohesiveness and plasticity. They hold a lot of water. But then we also have non-plastic clays like gibbsite, which is aluminum clay. We got allophane, halloysite. Those are highly weathered kaolinite. So kaolinite's weathered even further. That's no longer referred to as kaolinite. It's allophane or halloysite. So that's just just creating awareness here about clays. So here's the textural triangle. So here's the thing I was talking about. So you can see, based on the percentage of the separates, it's going to fall within a certain texture. Like loamy sand, you can see there, we're greater than 70%. So that's where we came up with that number. So if we look at soil texture groups, however, they're more than the texture. They cross. They're multiple textures. They cross. And I presented you with just the basics. There's actually some where it crosses the line. It doesn't actually fall right on the line with a soil texture, and we're not really going to cover that, but I just wanted you to be aware of that. So for the most part, a soil texture group includes those soil textures that I referred to, but this is a more authoritative source because, like I said, some of them don't fall right on the line. And so this gives you the amount of each material that can be in those soil textural groups and what the corresponding textural class would be. So if we look at soil texture versus structure, so soil texture is simply the proportions of sand, silt, and clay. So if we were to put that in a sedimentation jar and see how the sand settles out and the silt settles out, and I really don't like this part where it says clay, because a lot of times the clay doesn't even settle out. It stays in suspension. But it just kind of gives you, a graphic that each of those will settle out separately. And the sands, I mean, you can actually see like veins in the sand if it's widely graded, because it'll grade out the same way: the coarse sands, and then the medium sands, then the fine sands. So sometimes you can kind of see bands of that. So soil structure, on the other hand, is how there are clods of that material and how they relate to each other. So it's not just sand, silt, and clay, but it's how those things are put together to form what we call structural units, clods or microclods. And if we look at sand by itself, sand does not technically have structure because it's considered single grain, right? So but there is one thing to note about that. We do develop preferential flow pathways within sand. The sand particles actually will rearrange to form like conduits, if you will, that have coarser sand. So it's not a pore in a traditional sense, but from that distribution you can develop preferential flow pathways. So it kind of mimics some of the characteristics of structure in terms of how water flows between section of the sand versus the in between the sections where you have preferential flow paths. So again, what is soil structure? So if we just look at the volume composition of a desirable surface soil, and you guys have probably seen these before, this is very, very general. So we have 50% void space and 50% solid material, and the ideal soil, if you will going to be arranged so that you have 50% of your pores would be air filled. You know, this is after drainage, so this is kind of at field capacity. 50% of your pore space would be filled with air, or excuse me, 25% would be filled with air and 25% filled with water. And then 50% solid material, so most of that would be mineral, meaning, you know, quartz and kaolinite and things like that for feldspars, for different actual soil minerals. And then a smaller percentage, 2 to 5% typically, can be higher, can be lower, depends on the soil, but this is just an idealized, and that would be that organic matter. So why is soil structure important? So soil aggregation is important because water largely moves through the pore space between soil aggregates. So example, if we had a soil that was high clay, if there's no soil structure, then that becomes a pond liner. The water just effectively doesn't even move through it. But if that clay aggregates up so that there's void space between the various aggregates of clay, then we have soil structure, and then we get drainage and we get air movement. So the plant roots, likewise, they need air to grow, and they're going to dominate in the spaces between the clods or the aggregates. So that's the pathway that they're going to grow in. So aggregated soils are less compact than dispersed soils. That's a general term. They got more air because they have, or more void space because they have void space between the aggregates. And you can see here it shows these clusters of aggregates, but then it also shows that within those kind of aggregate units, there's also pore space in between the air. That's part of the you know, interpetal or within the clod void space as well. So why is soil structure important? So this is what I was just talking about. So with the clay. So clay particles, they have a negative charge and they'll repel each other. So that is not a good condition. So if we have clay particles that repel each other, we're not going to have structure. But if we have something that binds them together, like a cation, that will flocculate or make a bridge between them, then we can have aggregation. So that's an overgeneralization, but that's kind of the reason why. So if we looked at a dispersed soil, the particles, this would like be in solution, right? They don't flocculate together, but you know, when you would compress them, they would come together, but not as in a flocculated state, just in a massive state. That's why clay will make a clay liner. But if the clay is flocculated, then you can have highly productive soils. So the high charge density of cations, that determines how well the soil structure is and how strong the aggregation is. So for example, sodium is a cation, but it doesn't promote aggregation very well. So if we have a soil dominated by sodium, it tends to disperse the particles rather than aggregate them. But if we have calcium, magnesium, some iron, if we have multivalent cations, that's the polyvalent, they will tend to aggregate stronger. So we have the affinity of those cations to the exchange sites. So the more exchange sites that interact between, you know, two particles of clay, then the stronger the aggregation. So there's an exchange affinity for the cations. So on the left, these are the more strongly held ones. We have, hydrogen, aluminum, and we go down to serous calcium, magnesium, ammonium, and potassium about the same, and sodium is the more weakly held. Now that doesn't mean that, oh, well, if we got sodium, we can get rid of it easily. No, that's not necessarily the case, and we're not going to refer to that a lot in this lecture, but I have a few more slides that'll talk about that a little more. But sodium's a special case. But anyway, this is called the lyotropic series, and the strength of absorption is related to not only the charge but the size of the cation. So the bigger cations that have like a singular charge, they have less charge density, and that's why we see them more towards the right. That's why potassium, for example, it only has one charge and it's fairly large. But if we have calcium, that's a little bit smaller with two charges, so the charge density is much higher. So if we look at a pedal unit, a clod, if you would, soil ped, microped, we can call it many different things. So it's something that we need to look at on a micro scale in many cases. The basic unit can be very small, as we see here. There's a few grains of quartz there bound with some clay particle and organic matter. And so these little small pedal units, they can then be associated with other small pedal units to make a larger clod. But this is kind of showing you what's going on. We got the bacteria and stuff that are helping form some of the glues, especially with organic matter. We have interpedal void or airspace that's either holding air or water. And so how these all interact, this is what forms a soil ped as part of an aggregated system. So we can talk about these pads and define them in terms of their size and strength. So by size, and we're going to cover that on the next slide, but so we'll talk about that in a moment. But by strength, we look at grade or consistent. So the grade is such things as strong, weak, or medium, or moderate. Consistent, we look at how that condition is in various states: the moist state, the dry state, and the wet state. And the wet state is like, well, how sticky or plastic or non-plastic it is. So that's ways that we talk about soil structural aggregate strength. So if we look at the classes now, the classes are defined by certain sizes, and sometimes these are sieved. You got to handle them gently so that you don't break the peds apart to sieve them. But here's the general sizes for all of them. And if we look at how they're held together, we classify these aggregates, the morphology, by how they're put together. So like we talked about before, for single grain, we have sand, a soil structure blocky, slows the infiltration down a bit, but also holds more water. But if we move into platey, that's where we see more compacted soils. Then the rate of water movement is very slow. So now if we look at the bottom, this is as influenced by basically cations, or sodium in this case. So it's not going to affect the sand as much. That's granular, so we're going to have still fairly rapid movement. But the blocky structure, they tend to go to a prismatic shape, and we still have spaces between the pedal units, but the pore space that's within the ped is often compressed and compacted, and so the infiltration rate on those slows down quite a bit when wet, because they swell up. Now when they're dry and it's open and hasn't received a lot of rain in some time, initially you'll have a quick infiltration rate, then it'll swell up and it kind of seals off. So that can become almost, again, like a pond liner depending on how much clay is there and what the degree of sodium saturation is. And it can go all the way, especially if it stays wet, it could move all the way to the right and become massive so if you took this prismatic structure and you didn't change much of anything other than, when it's moist, put some compaction effort on it, you can quickly turn that into a massive soil structure, depending on how much load is placed on it. So if we look at sodium in the soil, sodium leads to poor aggregation. So if we look at how it interacts with the clay platelet, so we call that a diffuse double layer. I'm not going to bore you with that right now, but the sodium, that layer is very much wider, and so it doesn't allow the clay platelets to get very close together. It kind of pushes them apart, really. And so that's why we get that kind of a problem with soil structure and sodium. So saline soils, they have a high EC, but they tend to have a low sodium. Now we can describe them as saline sodic, and that's where the salinity and the sodium are both very high. And now the really problem soils is where we have sodic soils. So the sodic soils tend to have very much lower salinity, but the salinity that is there is, almost all sodium, if you want to think of it that way. So saline soils has a mixture of salts, which would be not only sodium, but calcium, magnesium, iron, potassium. Saline sodic soils are going to have the mix, but they're also going to be high in sodium, whereas the sodic soils, the overall salinity is low, which leaves a higher amount of sodium. So the sodic soils are the ones that, when we looked at the previous slide where they are prismatic, turning into massive with compaction, that's mostly going to be in the sodic soils. So the salinity is defined as the EC. That's one of the most common ways to define salinity, and that's decisiemens per meter. So if they have a high number, high EC, that's considered saline or salty, if you want to say it that way. If it's a low EC, then it's not saline or not salty. So it's pretty simple, but just something to clarify about that. So if we look at soil classification and how they're determined, so we have normal, saline, sodic, and saline sodic. So we can see the EC on the normal is low and the SAR is low. SAR is the sodium absorption ratio, so it tells us what the sodium status is. So it is flocculated. The saline soil is also flocculated, so the EC is high, but the SAR is low. And the saline sodic there on the bottom, both the EC and the SAR are high, but they're flocculated. The problem is sometimes people want to reclaim a saline sodic soil, and if you don't do it carefully, you preferentially leach out the cations and leave more sodium behind. So your overall salinity goes low, your EC drops below 4, but your SAR shoots up. So you can, in the effort to reclaim a saline sodic soil for higher productivity, if you're not careful, you can actually turn it into a sodic soil. And if you do that, then you got major problems with trying to do reclamation and bring that into productive state again. So the implications of cations on soil quality and water quality, they're also determined by potassium absorption ratio, magnesium absorption ratio, but those aren't really talked about much, but they do have a bearing on soil quality and water quality and soil quality. So most of the time we just look at the SAR and we assume potassium, magnesium is not a problem, even though they may be a problem, especially in reclaimed water and so forth. But just to make you aware that they do influence soil quality and water quality, even though we focus on SAR and the overall salinity or EC. So sodium and soil carbonates, they work together and have antagonistic influence on soil. So we just talked about what sodium does in terms of dispersing all by itself, But there's another insidious thing that they do, and they promote soil carbonates. Well, how do they do that? So, and why don't we like carbonates? Well, carbonates, we put carbonates on our soil, especially on the east. It's ag lime, and there's a lot of different names for it. Calcium carbonate, calcite, dolomite, which has magnesium, siderite, which has some iron, caliche, which is a contaminated form of carbonates, also often with both iron and magnesium in it, and it varies locally what its composition is, but it gets very, very hard. But just to make sure we're not confused, don't confuse soil carbonates, lime or limestone, with burnt lime, which is calcium oxide, or hydrated lime, which is calcium hydroxide. So we don't want to do that, and I see an error there. Calcium hydroxide is CaOH2 actually, but that's don't want to have any confusion though. So most soil carbonates are not pure, so they have contaminants of magnesium, especially dolomite, iron that's picking up siderite, and phosphate. So oftentimes there's not a lot of phosphate in terms of the total mineral, but there's quite a bit that can be sorbed either on the surface or actually part of the structure. They co-precipitate with carbonates, and they lower the solubility of it overall, of that resultant intergrade mineral, and it becomes harder. So limestone, is used as a significant ingredient in concrete. So it will harden up, it will become cementatious, and that happens in soils and creates cemented layers, and that becomes a problem. So even though the relative solubility is low, the effective solubility can be increased by grain size, and so carbonates can go in and out of solution. They can migrate, and they tend to recollect in areas where there's smaller pore sizes, like a compacted zone or a transition zone between profiles, an A and a B horizon, for example. So because they're not just sitting there acting inert, but they cause crusting and clotting and cementations, and they cause a lot of problems. And in addition to the fact that they tie up phosphorus, they tie up iron, zinc, manganese, and copper. They tie up the metals really well. Of course, because they're calcium, magnesium, sometimes they can tie up a lot of that too. Often there's plentiful calcium, magnesium, but not always the case. Sometimes they tie that up fairly well. At least they tie it up that we have an imbalance in terms of the availability of those minerals for plant uptake. So why do carbonates increase the sodium hazard? So clays are plastic and cohesive. We talked about that. So they not only provide nutrient exchange, but we talked about how they help form soil structural units. So the clays attract cations, especially if we're dominated by the polyvalent calcium, magnesium, iron. We have good structural stability. They flocculate. However, we get a bunch of sodium in there, they dominate. Instead of them leading to flocculation, they lead to dispersion. So dispersed soils lose their structure, they lose their drainage, they lose their aeration. So the sodium dispersed clays do not have good soil mechanical properties. And a lot of times the source of that problem from sodium and salinity comes from the irrigation water. So we got to remember that all mineral forms of sodium are soluble, and because of that, sodium can be the most dominant, like from groundwater, because there might have been a lot of calcium there initially, but a lot of times that becomes unsoluble, so it precipitates out of solution and leaves the sodium behind. So when the sodium gets high and there's in the soil, and we're moving water through the soil, because sodium is attracted to the soil like all cations, but the anion part, which let's just take sodium chloride, for example. But sodium chloride, the sodium's attracted to the soil, but the chloride's not. It's actually repelled by the soil, and therefore that anion will tend to leach and leave the sodium behind. And we get that charge separation, then it induces hydrolysis. And because of CO2 being in the water, it forms a sodium bicarbonate. And if that sodium bicarbonate can find a soluble calcium source, then it precipitates out as a solid that has low solubility, and when it precipitates out, it leaves the sodium behind, so the sodium can do its dirty work, if you will. And at the same time, that calcium carbonate is tying up other plant mineral nutrients, as well as semen in the soil, and causing a decrease in permeability and aeration and all those negative issues. And so, sodium is bad, soil carbonates are bad, and they do a tag team on us, especially in western soils and other irrigated soils. So if we look at soil pH and flocculation, so acidic soils are often well flocculated. So hydrogen is known to be a strong flocculant. So even though it's only one charge, it is so dense and it's so small, it allows for that, what we call that diffuse double layer between clay particles, to be quite small. And so if we look at that, we can see that the protons, or the H plus, is going to have stronger soil structure, and intermediate is calcium, and you could put magnesium in there. This is just a general from this one study. And then sodium is last. So if we look at that study that I'm referring to here, it shows you how well that why we got that chart on the bottom, because we look at the flocculation ability of each of these cations. So if we look at the poor flocculators versus the good flocculators, so this is just a review. Sodium is poor, calcium, magnesium are pretty good. Potassium is in between, so it's kind of poor, but it's not as bad as sodium. But that's why I said in some circles, especially in the early days of studying saline soils, they definitely looked at the potassium absorption ratio in particular as being an indicator of poor quality water or soils, for that matter. And then if you look at magnesium, it's same kind of general trend. It's not near as good as calcium. So sometimes if you have too much magnesium, you kind of lose some soil aggregate stability. So soil water holding capacity. So just want to talk about how that's influenced by clay and by structure aggregation. So large soil pores conduct water, they drain. The medium ones retain water, they conduct water more slowly. And the small pores are the capillary pores, they retain water, and we're not going to get really gravitational flow to get those to drain. So soil water moves through capillary activity due to the matrix potential, and always moves from wet to dry. So that's the gradient that drives that water movement. And if we look at the influence of sodium on that, so the large and medium pores in heavy textured soils is due to interaggregate structure, and especially in finer grained soils, they depend on the aggregation, and sodium destroys it. And so therefore we lose our infiltration. We don't hold as much water, but at the same time, we're often waterlogged. So it increases the water holding, maybe not the overall water holding, but the percentage of water. In other words, the total pore space goes lower, but the proportion of the fine pores that hold the water increases, because the large pores that would normally hold air have disappeared, if you will. So now if we look at the chart, just to show us a general in numbers, the the relationship of EC versus SAR. So we see that within a range we have no reduction. In the intermediate we have a moderate, and then we have a severe reduction where we have low EC and high SAR. And this is for soils that contain appreciable fines. If this is a sand, you know, we don't see this because sands, single grain, they don't really disperse. And we're not going to cover it in here, but there's other issues that with sodic sands, but we're not talking about that here. So this kind of chart is just for soils that contain an appreciable amount of fines, particularly clay. And so now just a pictorial, and this is our last slide. This is just a slide from you know, the Middle East region. If we look at a sodic soil before the rain, you can see all the cracks. And these would be massive soils, not a lot of air movement, but some of those cracks may take some water initially when we get rainfall. But by and large, it's going to be like a pond seal. So after rainfall, we got ponded water, and that's just the way they work. And so those are the kind of things that we avoid. So we're going to want to talk a little bit more about growthful and how it impacts these different things. So we needed this background to do so. All right. Thanks, folks. We'll catch you on the next one.